team purchased a FANUC robot arm and a conveyor belt that they integrated into the developer kit. They selected a shunt gripper that you can see in the bottom right and designed the teeth that interface with the threads of the round. They also developed pick and place scripts that they execute from the included teach pendant. Their recommendations for us this year were to operate the arm from non-proprietary hardware and software. In other words, get the code off the teach pendant and run it from an external laptop. Our problem statement for this year was to design and build a proof of concept automation cell that automates the manipulation of 155 howitzer rounds during manufacturing to improve production efficiency and reduce physical strain on factory workers while maintaining operator safety. Our requirements for this project was to automate pick and place of 155 rounds. We needed to include features that ensure operator safety, and we needed the system to be modular for future teams to add on. We're constrained by the arm that was purchased by last year's team, and we also had to be able to disassemble the system and transport it. This is our overall design for the automation cell that we came up with this year. There's many subsystems in this design that the 8 of us all worked on. Here's a demonstration of the cell. So you'll notice the main chassis holds the robot arm. It has all the subcomponents, including the robot transformer at the bottom, including the control box that are each cadets made. And you'll see an operator places a cart into the system, and magnetic locks lock the cart into a specific place. There's an HMI, a human machine interface, for the operator to start pick and place scripts. You'll see here the robot arm will pick rounds up from predetermined locations in the cart and move them onto the conveyor belt.
So the programs that we used for this process is RoboDK. What it does is on a laptop we can create a simulation of this process, test it, and then we use user socket messaging from the FANUC side, TCP, IP, Ethernet connections to communicate between our laptop externally to the FANUC arm and execute this in reality.
We'll let the video run a little bit longer just to see a picture of what our current system is made for. And one of the big things about this is it takes us 14 seconds to move around off the cart and onto the conveyor belt, which is almost twice the speed of the workers in the factory.
As you saw in the previous video, the chassis is going to be the main component of the automation cell. And it's going to, Miles said, it's going to be responsible for housing not only the robot arm, but its subcomponents and the control box itself. So we decided to make this chassis primarily out of T-slotted extruded aluminum because it's highly modular and easy to work with, and it allows future capstone teams or the factory itself to really modulate the system and fit it to their specific needs. And then as for holding the robot arm, we decided to go with an aluminum base plate because it was both light and strong enough to mount the arm on to ensure that it does not budge during operations.
The docking system includes Delrin bumpers that align the cart in a fixed position. We also purchased a magnetic shear lock that holds the cart with 2,000 pounds of force. Sensors that are integrated into the Delrin bumpers detect when there is a cart in place and signal the control box to turn on the magnetic lock. We made 2 major design choices when designing the docking system. One is a fixed versus variable position. A variable position would require us to use vision scripts to locate the rounds in the cart, versus a fixed position allows us to just execute pick and place scripts with predetermined locations for each round. We also decided on a magnetic lock over a mechanical lock, 1 for simplicity, and 2 so the control box can easily turn on and turn off the locking system.
And now on to some of our main safety features. The largest safety feature we have is just a physical barrier between the operator and the robot's area of operation, that being our plexiglass barriers and the plexiglass doors. We also have sensors on the doors to detect if the doors are open or closed, and this will allow us in the future to, when the door is open, stop the robot due to system interrupt. We also have an emergency stop button, which when pressed will cut power to the entire system. And when the robot loses power, it will lock into place, and a spring-loaded U-boom gripper being spring-loaded will maintain hold on the ground throughout power loss. The main design choice we had was doing an open versus closed cell. At the end of the day, we chose closed, and this is our current system, as you cannot physically get into the robot while it is operating. An open cell would be like using laser gates or tape just to designate the areas of the robot's operating. Now to the control box, it powers the entire automation cell from 120 volts AC, passes the Raspberry Pi, and runs Python scripts and RoboDK. It essentially is acting as the entire brain for the automation cell, connecting robots with power and signals, mag log, and all the sensors. It also has circuit breakers and surge protectors for all three of the different rails within the control box. And this, again, is just another safety feature that we included. The main design choice we had with the control box was to ensure that its factory is safe. That being that just it's fully enclosed and you can't like drop something in it. Yeah.
So there's three main components of the software side for this project. The first being the human-machine interface. This includes login and authentication criteria. This is another added security feature from the software side. Within this, there is a limited number of login attempts as well as a timeout feature. If the user steps away from the system for too long, it will go to sleep or turn off, and the user will have to re-authenticate. Once the user has successfully authenticated, they'll navigate to the home screen where they can select two different paths. One is they can just run the simulation itself as a whole, or they can manually move the robotic arm with predetermined scripts that we wrote. If the arm is in an unsafe position or if it needs to be transported for some reason, we've added that feature as well. The next feature is computer vision. So we used a RealSense camera. Originally, we had a calibration script that we use to determine the 6 positions for the rounds to be picked up. The camera has depth sensing so that once the 6 rounds are in the cart, we can use the camera to locate which rounds are available and ready for pickup and which slots are empty. We use this as Python script so it can be easily integrated with the rest of our RoboDK features. Finally, our RoboDK it's sort of the backbone of the software side for this project. A few important features are joint movements and linear movements for the robotic arm, as well as controlling the speed, externally controlling the gripper. RoboDK offers live video feed simulation, so while the physical arm is moving, you can watch the simulated arm move as well. Along with this, there's path tracing, so once the simulation has been completed, it will show the path that the simulated robotic arm took, and you can compare this to the path that the physical robotic arm took to see if there was any discrepancies or if any errors happened during the simulation. Another important feature is it displays active connection feed between the arm and the simulation. So if by chance the connection is broken, the user can easily see that, reestablish connection, and continue the process.
So the current state of our capstone, we did automate pick and place of Palantir shells. We've incorporated safety features into our system, and it is modular, and we have documentation to support future teams in this capstone. We recommend that future teams can take on a number of challenges. First being state machine code, and that's integrating sensors, the stack light that we have, and cart release conditions all into one state machine algorithm. There is room for improvement on vision side. There is an overhead camera that's mounted above the cart, as well as an end of tool camera that's mounted directly onto the robot that can be utilized for vision algorithms. You can add more operations into the system, and like weighing the actual rounds, etching, or it's visually inspecting. You can use the end of tool camera to visually inspect the rounds. There's a LiDAR unit that's in our system that we did not touch this year. That's available for next year's teams to integrate. And cable management is a big one. There's a lot of room for space optimization in case future teams need to add additional components into the system. At this point, that concludes our presentation. Open the floor to
So kinematically, a robot arm is kind of complicated in terms of planning out motion. Was your team constrained to use a robot arm, or is there a reason why you wanted, or why you chose to use one?
Yeah, so we were constrained to use, last year's team purchased the Fanic arm, I believe for about $60,000, so it's not, let that go, yeah, we had to use a robot.
So I guess the follow on, are you doing anything to optimize the path of that robot arm as it goes from pick to place, or how is that working out?
Yes, sir. So right now, RoboDK is super simple and easy to use. You can, within RoboDK itself, you can try out the simulation to determine those positions, and it can easily be optimized. Right now, we have basically a centralized point that can pick up each of the 6 rounds, and it takes it to a centralized point above, so there's no collisions between the rounds when it's picking it up. That could easily be optimized.
In the demo, you had the robot picking up just like some head, like not a full round, but just like a model head. How would the additional weight of picking up an actual full round? Do you think that would have any effects on the trajectory of the joints within the arm?
So this robot arm has a max weight that it can pick up of 7 kilograms. A full-size round is around 100 pounds, so that's not something we can do, and even the half-size rounds are too heavy for the current robot arm. So this is the best we can do with the current. Yeah.
But in a realized system, the weight should not affect the trajectory of the joints. I think I get your question. Added weight.
Okay, so then as a follow-on question, have you identified available robotic arms that would be able to handle the weight of a full-up round?
Yeah, so yeah, Fanic makes much larger arms for industrial, like they make arms for manufacturing cars, for example, and sizes in between, like our arm and that. We haven't identified exactly which models, but there are definitely available rounds that work with RoboDK and the current systems of it.
So would the software be adaptable?
Yes, sir.
Okay.
Ken Kraetzer, Cadets Media. I just, so much you hear in the news about the need to increase scale on producing 155 howitzer rounds. Does this help with that, being able to, speed production, or is it primarily a safety asset to production?
Absolutely. So automation enables this machine to work day in, day out without stopping. And right now it's just a pick and place operation, but we see this project in future years to accomplish more tasks along that process, with the hopes of like a fully automated production plant that I believe IAAP is currently constructing, and that will greatly increase production rate of howitzer shells.
Thank you.
What is your system reliability? Have you measured percentage of success and how you handle the failure, especially the pick at place that is you insert that you expect either using hydraulic or the compressed air?
Yes, so early on, we had some troubles with the gripper itself and navigating to the correct position. But as of late, we've had close to 99% trajectory because of the precision of the Fanic arm accompanied with RoboDK.
So if it fails, do you retry or?
So if it fails, the system will emergency stop, and an operator can come in, read any error statement that it says, like if determine what the error was. If it fails to pick the round, and you can just restart the simulation from there, and it can pick up exactly where it left off.
Are you saying that the common failure mode is just alignment? You're not able to find the hole to insert?
Yes, sir.
What about the force? Because when you have the heavy shell and the place that pick the head you insert there, regardless of how much of the weight the arm can lift, but that is, you have to have the force to expand it, then you load it up, right? So have you tested what is the mechanical design of that piece to be able to sustain that load?
No, we have not. We're currently just working with 3D printed half rounds. That's by limitation
But
of the arm.
conceptually, do you think the compressed air is enough or a hydraulic system is required?
We don't know yet. That's
Okay.
Yes, sir.
So I guess thinking about the supply chain of the supply chain, if we were to try and ramp up production using the system in the midst of a trade war, where do the FANUC arms come from, and would we be able to procure them?
Not sure.
All right, well done, gentlemen.